This is my kind of a run through of Bellman-Ford's algorithm with a bidirectional graph with 9 nodes. So here's our example graph. We've got our nodes, we have our directions and our weights or distances, and here we have our distance labels for each vertex. So as per the algorithm, we iterate through each of these vertices n-1 times, which is 8, or until the distances are not updated in that iteration. And again, as per the algorithm, the distance is set to 0 for the first vertex or node, and the rest is set to infinity. So we start with node 1, and then we check its outgoing nodes, and we add those to the list. And then we go to node 2, check its outgoing nodes, update those. And we go to node 3, check its outgoing nodes, or outgoing edges. So this one is, let's look at 9. So 9 currently has just been calculated as going from 1 to 2, 2 to 3, and 3 to 9. So 3 plus 4 plus 7 is 14. So the next node we're going to look at is 4. And 4 takes us to 9. Here we know that it took us 3 plus 4 plus 5, which is 12, to get to 4, and 4 to 9 is only 1. So the distance to get to 9, this path, rather than going straight to 9, we go 1, 2, 3, 4, 9, is less than what we already had recorded. So we had initially it was 14, but now we can see that actually we can get there in 13, so we update 9. So next we're going again down the list. So we're at 4 before, now we're at 5, and we update this is to get to 7 and to 8. Next we should be looking at 6, but we don't know how to get to 6 yet. The only incoming edge is from 7, and we haven't been to 7 yet. So since we have no way of calculating how to get to 6, we leave 6 as infinity. So we skip to 7, and 7 now we've found a way to get to 6. So we update 6, and this minus is important, we'll look at soon. So then we go to 8, we update 8, and then we finally go back to 9. So we have iterated through all the vertices once. So now we iterate through it again and see if we can update any of the distances. So I've just changed some colors to make it clear that we're going through this as a second iteration. And so we start with 1. Again, green represents the one we're looking at, or the one we are at, sorry, and blue is we're just seeing if we can update any of these. So now when we look at 2, can we update 3 or 5? No. When we look at 3, can we update 12 or 13? No. What about 4? This should have 2 in blue, sorry. And we've got 5. And now earlier we couldn't look at 6 because we didn't know how to get there, but now we know, looking at 6, we know that the cost of getting to 6 is apparently 6. So when we look at 5 and 8, we found a quicker way to get to 8 than we knew of before, because we can use a path via 6 plus 6, which is 12. So we update 8. And now we're looking at 7. Can we update any? No. Now we look at 8. And then we look at 9. And so now we've iterated all the vertices through twice. And during the second iteration, only one distance was updated, and that was 8. So if we were to iterate through one more time, we would see that no distances were updated. So this is what our shortest path tree would look like prior to post-processing. We would see that to get to 8, you'd have to go through 6, which has to go through 7, which has to go through 5, which goes through 2 and 1, and then 9 goes through 4, which goes through 3, which goes through 2 and 1. But the post-processing involves looking at the vertices I'll just read through this. So since the distance to 6 is less than the distance to 7, and we have to go through 7 to get 6, 6 is updated to minus infinity. And then again, this is repeated for the nodes that are connected to 6, because if 6 is minus infinity and you can get to 5 from 6, 5 is also updated to minus infinity, and as with 8. So because these are all connected with each other, all of these get their nodes updated to minus infinity. So when we look at our shortest path tree, this one should say post-processing, these are undefined. They're an undefined path because they contain negative cycles. So we're left with our shortest path tree, which is just 1 to 2 to 3 to 4 to 9.